Welcome to part one of this last series into longitudinal designs and structural equation modeling. In this lecture, I'm going to introduce you to longitudinal designs, and we're going to take most of our time talking about autoregressive models. In part two, which we'll cover in the next module, I'll talk about growth mixture modeling and latent growth curve modeling. So to start off with, when I get into working with longitudinal designs, this quote from Little, Preacher, Siegel, and Card comes to mind. Todd Little is one of the foremost statisticians who has done a lot of the work on structural equation modeling to help us have what we have today. So in their book, they say, models are simply convenient mathematical or schematic representations of theoretical predictions. Although no model is ever strictly correct, many models may provide useful approximations to the truth. So in other words, when we are doing structural equation modeling, we're trying to model out what's happening in the real world through schematic representations of theoretical predictions. One of the things that we often have in our theoretical predictions is temporal or sequential sequencing of variables. Longitudinal designs help us get one step further to actually testing those sequential ordering, the sequential ordering that we have in our assumptions, theories, and hypotheses. So the purpose of doing longitudinal design is to help us move one step closer to causality. Keep in mind that causality takes more than just longitudinal research. There are many other pieces in it. However, longitudinal designs are necessary, although not sufficient, criteria for determining causality. Without temporal ordering, when you're doing your models, you could flip around variables in whatever order and get the same results. So you can flip an IV and a DV and you'll still get the same results, much as you would with doing multiple regression in SPSS. Once we have temporal ordering, then we actually have something more than just theory for the sequential ordering we have in our model. When we're doing longitudinal designs, there are some things that we also are asking about. Most specifically, we'll see this in autoregression, in our autoregressive models, and also in our latent growth curve modelings, that we are really looking at stability and also change across time. So we'll ask research questions about what's the association or what's associated with changes in variables across time. What does the stability of variables look like across time? In autoregressive models, we're really looking at stability of variables across time. In latent growth curve, we're looking at trajectory and changes in variables across time, and what kind of covariates, or in other words, what kind of other variables account for changes, either instability or changes in trajectory across time. So in longitudinal models, we get to ask new and different kinds of research questions that you are unable to ask for when you are just doing cross-sectional research. So cross-sectional research is when all the variables are assessed at the same point in time. But if we have longitudinal research, we can ask those interesting research questions about change in trajectory and also change in stability across time. So for example, we may be really curious about what causes changes in alcohol use across time, or what causes changes in trajectory of relationship satisfaction across the transition to parenthood. When we're thinking about causality, there are a few things that we need to keep in mind. There are three specific threats that I want to cover today about that can get in the way of causal inference. One of the reasons why when we are doing longitudinal research that we need to remember that causality is only implied in longitudinal models, that there is much more. Three of those threats to causality are the exogeneity assumption, omitted variable, and proxy variable problems. The exogeneity assumption relies on the fact that there might actually be some other true causal agent may have occurred at an earlier point in time. So this isn't the first step in the causal sequence of ordering of variables, but there's something else there. The omitted variable problem is that we have forgotten or neglected to include other variables that are related and covary along with our variables in our model. And the proxy variable problem is that there's actually another variable in the background that is actually causing this, and the variable that we have is just a proxy construct. So while longitudinal designs are a critical step towards determining causality, there are many other factors to be included beyond longitudinal design to determine causality, but it is a very important step forward and a necessary step. And also there are other kinds of research questions that you cannot ask unless you are doing longitudinal design research. So next I'm going to talk about the two of the basic kinds of longitudinal designs. So basic longitudinal designs and then autoregression. And then latent growth curve we're going to save for the second set of lectures in this module series. So basic longitudinal designs are just where you're doing any kind of SEM, but you actually have temporal sequencing. So this is any kind of structural equation modeling that we've talked about thus far, whether you're doing multiple sample, dyadic, path analysis, whatever it may be, and you're just making sure that your models, the variables in your model, have temporal sequencing in them through longitudinal design. So this example here on this slide comes from a paper that I did with Cole Ratcliffe and Jared Durchie, in which we were looking at the relationships between relationship quality, positive engagement, and negative child behavior. And you can see here this is kind of a quasi dyadic data analysis because we do have matched mothers and fathers in this data set, and then we're looking at the impact of those on negative child behavior across time. When you're doing these longitudinal designs, if you think about these variables as existing, if you look at the vertical alignment, you're going to have first relationship quality, which we take at age 1. Then we have positive engagement, age 3, then negative child behavior, age 5, and then again at age 9. So the IVs are going to come from their first wave, and then your next set of DVs, or in this case our intermediate variables of positive engagement and negative child behavior, those are each going to come at different waves as you move forward. So you're going to take the variables from those waves so that you can have temporal sequencing. And then everything else that you do in these models, you follow what we've talked about previously in this semester. Autoregressive models are a specific kind of longitudinal design in which you're really assessing stability over time. So if you're really wanting to know about stability of a variable across time, you're going to be doing an autoregression model or an autoregressive model. So in this, we're going to collect data from the same variable across time. The real work being done, as you've seen in other stuff we've done with multiple sample and also with dyadic analyses, the real work in actually testing these models is in doing constraint testing. So again, with autoregressive models, the main purpose is to assess paths between the same variable across time in order to determine the stability of that factor or that variable across time. And when you're looking at covariates, what is related to change in those variables across time? In the most basic autoregressive models, you're just going to be looking at the association between time 1 of some variable with time 2, and then time 2 with time 3, time 3 with time 4, and so forth. So we're not going to be looking at time 1 on time 3, or time 1 on time 4, or time 2 on time 4. We're just looking at that path in between each segment of time. If the stability of that factor is perfect, then we would see that the path loading would be 1, because that would mean 1 standard deviation increase in time 1 equals 1 standard deviation increase in time 2. Or 1 unit increase in time 1 is equal to 1 unit increase in time 2. And 0 is having absolutely no stability. Now typically we're never going to be at 1 or 0 because we're in social sciences, but as it gets closer to 1, we're going to see more stability. And also as we see that those, when we're looking at more than one time point, like in the example here where we have time 1 for dedication, time 2 dedication, time 3 dedication, 0.68 and 0.77, if those two are significantly different from each other, then we're seeing a significantly different model across time, or significantly different stability across time. Or if that 0.68 and 0.77 are not significantly different, then we can see that it is stable across time. So what we're going to be doing in our constraint testing is constraining those two corresponding paths to be equal. If our model fit gets significantly worse, then those are significantly different. So one kind of autoregressive modeling is when we do multiple indicator autoregressive models. So this is when we have latent variables, and that what we're actually doing, like in the previous example here where we have time 1 dedication, time 2, time 3 dedication, these are actually latent variables rather than manifest variables. That's a multiple indicator autoregressive model. Typically in write-ups they won't say multiple indicator autoregressive, they'll just say autoregressive. So in this model, we're really looking at that latent variable moving at time 1 to time 2 to time 3. We're looking at the stability of that across time. When we're doing this kind of using latent variables in autoregressive models, there is a specific application that makes this much better than traditional methods, and that is actually doing test-retest evaluations. So when we're doing that, rather than doing traditional like Cronbach's alpha or chi-squares or other kinds of things, we can actually, one of the reasons this is much better is that we can account for a few things. Number one, we can assess measurement invariance over time. So we can actually account for measurement invariance in that test across time. Number two, we can account for measurement error. So the uniqueness of each indicator can be correlated with each other across time to account for measurement error. And then number three, the loadings of the same indicator can be constrained over time, so the only instability, the only thing freely estimated, is the change in the factor across time. In these next slides, I'm going to show you an example of this and how this works. So let's take, for example, if we gave an assessment of dedication to studying structural equation modeling. And we did this at the beginning of the semester, midway through the semester, and the end of the semester. And I'm going to give you the same assessment at each three of those time points, and it has 4 items. So that's where here you can see we have D1, 2, 3, and 4. Those are our 4 items for our dedication survey. And we have those at time 1, time 2, and time 3. And when we do our autoregression model, or autoregressive model, we will correlate the corresponding items. So D1 with D1 across all 3 time points, D2 with D2 across all 3 time points, and D3 with all 3 time points. And what we can also do is constrain each factor loading to be equal with its corresponding factor loading across time. So for example, you can see here I've color-coded the correlation. So we can actually correlate this. And when we correlate each of these factor loadings, we're actually correlating the error term, not the actual item there. So this accounts for measurement error. So we're going to correlate the measurement error of that first item across time 1, time 2, and time 3 for each of those. And then on this slide, you can see that you can constrain the factor loadings, each corresponding factor loading. So, for example, that D4 to D1, so that time 1 dedication to D4, time 2 dedication to D4, time 3 dedication to D4, we can constrain each of those to be equal, and that will account for measurement invariance across time. So any measurement invariance, so when we're doing this, we can account for both measurement invariance and also measurement error by constraining the error terms to be equal. That's what I have on the bottom here, is we're constraining the error of each item. So our 4 items, D1, 2, and 3 across time. And then we can also constrain our factor loadings to be equal in order to account for measurement invariance. And then the only thing being freely estimated are those paths from time 1 dedication to time 2 dedication, and from time 2 dedication to time 3 dedication. And we can really assess stability while accounting for measurement invariance and measurement error. On this next slide, I have the syntax for what this looks like. So here's the syntax for that. I've kept in my notes here as well to show what each set of syntax are doing. Starting at the top there, we have our model CFA. So we have time 1 dedication by the time 1 dedication 1, 2, 3, and 4. Time 2 dedication with the time 2 dedication 1, 2, 3, and 4. And then time 3 dedication by time 3 dedication 1, 2, 3, and 4. And that's going to set up the latent variables. And you can see in here I've added in constraints. You can use letters or numbers, it doesn't matter. In this case I've used numbers here, so 1, 2, 3, and 4, to constrain each factor loading to be equal with its corresponding factor loading at each time point. And then next I have the autoregressive syntax, so this is T3 dedication on T2 dedication, T2 on D1, and that's going to be the direct paths, the only thing that's being freely estimated here. And then lastly, I have the correlation terms there. So time 1 dedication with time 2 and time 3 dedication, time 2 time 1 dedication 2 with time 2 and time 3 dedication 2, and then time 3 with time its corresponding variables as well. There we go. I realized I was missing the fourth variable there with the correlations. So I have all the correlations put in there. I have the constraints for the factor loadings, and then I also have the autoregressive syntax in there. So that is how you would write out the syntax for this model here. Sometimes, and oftentimes, we want to know what is correlated with change across time. So when we do that, we can add in a covariate. Testing covariates really help us to get at more interesting questions as well about what accounts for or impacts changes in stability across time. So for example, we may look at competency in doing SEM. That perhaps as you get more competent, you become more dedicated to doing it. So we can do that by taking competency and then regressing it onto each of our variable at each of our time points. We may take, for example, teacher efficacy and see how that impacts dedication across time, the stability of that across time. When we're testing covariates, there are two ways we can do it. And you've already been introduced to one of these ways earlier in the semester. So if we have a nominal or a categorical variable, we may want to do multiple sample SEM where we test our covariate as a grouping variable. Or if it's a interval ratio variable, we may just include it as another manifest or latent variable in the model and then regress that onto our variable at each time point. There is one other kind of specific autoregressive model, and that's the cross-lag autoregressive model. And the cross-lag autoregressive model is really when we have two sets of variables that we are interested in assessing stability and also want to look at the interaction, or in other words, how they impact each other across time. So we're testing the stability of two variables and their effect on each other. So the cross-lag part is that effect onto each other. This helps us to answer questions like, what is the concurrent association between the two variables at time 1? What is the stability of the two variables over time? And do earlier levels of one variable predict later levels of another variable, and vice versa? So in other words, one reason that cross-lag autoregressive models are so helpful is they help us to get at bidirectional causality, because we're looking at the impact of each variable on each other across time. So here is an example of an autoregressive model. So we have alcohol use and parent-child conflict. When we do these, it's very common that you're going to have an association, so that with statement, a correlation between each set of variables at the same time point. Similarly, you saw this earlier in the example I gave in the basic autoregressive model or basic longitudinal model. You would have seen a correlation between two variables at the same time point. This is also often helpful because there is shared error variance in each of those variables in their association at each time point. So in here I've color-coded this to show you the different corresponding associations that we're looking at. So the blue line here is adolescent alcohol use onto itself, adolescent alcohol use at each time point. The yellow is parent-child conflict onto each. And then the green and that purple is the cross-lag portion. So that's looking at parent-child conflict onto adolescent alcohol use, and then back onto parent-child conflict later on. In the other one, we have adolescent alcohol use onto parent-child conflict and then back onto adolescent alcohol use. So that gets us, so we're looking at that bidirectional impact. The green arrows here are parent-child conflict onto adolescent alcohol use at each corresponding time point. And the purple is from adolescent alcohol use onto parent-child conflict. So when we're looking at constraining corresponding paths, these are the ones we look at constraining and then testing to see if they're significantly different. Again, if our model fit gets significantly worse, then that means that those paths are significantly different. So this here is the syntax I have for the model I have put right here on this slide. So where I'd have like my time 3 alcohol use onto time 2 alcohol use and conflict, time 3 conflict onto time 2 alcohol use and conflict, time 2 alcohol use on time 1 alcohol use and conflict, and then time 2 conflict on time 1 alcohol use and conflict. And then I also have the constraints here. If I were to constrain each pair of those colored models, so each pair of those colored arrows, each pair of those colored arrows, so the blue corresponding to be the same, the green constrained to be the same, the purple constrained to be the same, and the yellow constrained to be the same. I have that in here. Again, you can use letters or numbers, it doesn't matter. And then at the bottom here, I have my correlations between each corresponding time point. So again, here's the syntax you'd have for your model syntax for this model here. So that covers autoregressive models. In our next module, we're going to cover growth curve modeling.